Hey everyone, welcome back. This is Paul, and what I want to do in this video is give a reason why you cannot create an actual infinite from successive addition. So you can see I'm moving apartments, so I'm living out of boxes and unpacking, and figured I'd make this video to take a break. I actually enjoy doing this stuff. So yeah, then back to unpacking boxes. Anyway, so if you saw my last video, what I tried to do was give reasons to doubt that an actual infinity could exist metaphysically. This video, what I'm going to try to do is give a more proof-like argument against building an actual infinite from successive addition. I'd like to thank my lab mate Lorenzo for showing me Dr. Wildberger's channel. The main analogy here comes from Dr. Wildberger's arguments. It comes from an analogy that he gave, and I'm sort of co-opting it and modifying it slightly to be an argument against forming an actual infinite from successive addition. So yeah, has implications for the Kalam though. I'm not really focusing on the Kalam today. Yeah. So if you recall the Kalam, or Dr. William Lane Craig's version of the Kalam cosmological argument, he argues whatever begins to exist has a cause. The universe began to exist, therefore the universe has a cause. Those are kind of the main three premises that people know. And then he argues the temporal series of events is a collection formed by successive addition. You could definitely push back on this point, and I know Morstan does. 5, a collection formed by successive addition cannot be an actual infinite. And then he concludes from 4 and 5 that the temporal series of events cannot be an actual infinite. So what I'm focusing on is purely point number 5. And if you deny premise 4, then you don't need to conclude 6. So what I'm really doing is giving an example why a collection formed by successive addition cannot be an actual infinite. And Morstan actually doesn't make this claim, although I originally thought he did. He doesn't go through this. Instead, what the argument Morstan makes is, well, maybe we have the temporal series of passive events is and was always an infinite collection, and it never had a first element. And if that's the case, if that's the point that somebody's making, if that's where they take an issue with Kalam, then I think this argument won't convince them. But if they do accept that I guess there had to have been a first element in the temporal past, then this argument would have implications for the Kalam. So one technicality here actually involves how you define infinity or infinite. I tend to think of infinity more as this idea, as this sort of carrot on the stick. When you're on a treadmill, it's always greater than this sort of infiniteness, not pin downness. Oh, actually, I kind of reject Cantor's whole thing of transfinite numbers. I think it's a little bit of a mistake. But if you are going to accept Cantor's transfinite numbers and premises, and I realize I'm a little bit of an outlier there, then I think this video will be quite interesting to you. And yeah, I will also say I used to be a mathematical Platonist. I mean, I love math, and I used to really accept a more realist position on it because I really liked it. I'll be honest, it was because I liked it and I thought it was beautiful. And I think learning a lot more about math, especially things like the incompleteness theorem, these sorts of things, I started maybe becoming a little bit more skeptical. Like, yeah, math is beautiful, but it's also weird. You know, it's also kind of a strange thing. So maybe in that case, I guess I'm agnostic about whether these things can actually exist and whether an infinite can exist. But I definitely don't think you can form an actual infinite from successive addition, and we'll talk about that in this video. And this is a point Quentin Smith actually makes. So in this reading, and I totally forgot where I found this. I took a picture of it, and then I forgot where I actually found it from. But Quentin Smith argues, although an infinite series can never be completely synthesized in a finite time, it can be completely synthesized in an infinite time. So here, basically, the thing is in an infinite amount of time, Quentin Smith argues you can create an actual infinite. So let's, I'm going to show why I don't think that's possible. So imagine the following. You have this collection of balls, an actual infinite collection of balls. And even though this is similar to Hilbert's Hotel, I guess you would call this like Hilbert's balls, or can't call it that. I guess now I have to call it that. Okay, this analogy I'm going to call Hilbert's balls. It comes from N.J. Wildberger. You have an actual infinite collection of balls, and you have these two boxes, box 1 and box 2. And these are special boxes in the sense that they can actually hold an infinite amount of items or balls, what it's going to be. And to start out, what I'm going to do is I'm going to take balls from this infinite collection, 10 at a time, and I'm going to put 9 of them in box 1, and I'm going to put the other one in box 2. And we repeat this process, take 10 balls, put 9 of them in box 1, put one of them in box 2, and we repeat this process over and over and over, all the way to infinity. And at the end, or after an infinite number of times, as Quinton Smith would argue, but you do this really fast and you do this again and again and again, what do we have? At the end, we're going to assume for the sake of a contradiction that we can, in an infinite amount of time, completely synthesize an infinite collection, which means there are 0 balls left in this pile. How many balls are in box 1? Well, an infinite, because we literally took an infinite number of balls and put them in box 1. How many balls are in box 2? Also an infinite, because we also took an infinite number of balls from the pile and put them in box 2. So there's no contradiction here. I think this is very clear. This makes sense, right? You take your infinite collection and you just kind of split it up, and you're probably wondering, well, why did you use 10? You could have just done 1 and 1. We'll get to that in a second. So this makes sense. This all seems fine. Let's do this analogy again, but let's do something slightly different. We're going to take 10 balls from the pile, just like we did before, except this time we're going to put them all 10 of them in box 1. Then what I'm going to do is I'm going to reach into box 1 and I'm going to pull out a ball and put that ball that I pulled out into box 2. So after the first step, there are 9 balls in box 1 and 1 ball in box 2. And we repeat this process, put all 10 balls in box 1, take one out and put it in box 2. And you do this again really, really fast. You go all the way an infinite amount of time. How many balls are left in the pile? 0. Now here's where things get interesting. How many balls are in box 2? An infinite, right? Because we took an infinite number of balls from box 1 and we put them in box 2. Totally makes sense. How many balls are in box 1? This is weird. I can actually tell you however many balls I want there to be in box 1, and that's how many there are. So for now, I'm going to say I want there to be 2 balls in box 1. And that's what it is. Now let's see why this is the case. If you believe in Cantor's transfinite arithmetic, there is no contradiction here. And let me explain why. Let's go inside box 1 and let's see what's going on. So I first put in 10 balls into box 1. And what I've done is I've labeled them 1 through 10. So just labeled all the balls 1 through 10. The ball that I take out, if I want there to be 2 balls in the box, well, actually the reason is because when I took the ball out of box 1 and put it in box 2, I took out ball number 3. Then when I put in the next 10 balls, and I'm going to label them 11 through 20, the ball that I took out was ball number 4. And we do this again and again. I keep putting 10 in, and I've put an infinite number of balls inside box 1, and I've taken an infinite number of balls outside of box 1. And at the end, if you do this for an infinite number of times, or for an infinite amount of time, you're left with 2 balls in the box. But of course, you can actually change this. Let's say I want there to be 5 balls in box 1. Well, that's fine too. The reason is because when I put the first 10 balls in the box, I labeled them 1 through 10 like before, but this time when I reached down, I pulled out the ball labeled number 6 and took it out of the box. Then I put in the next set of 10 balls, labeled them as such, and took out ball number 7. And after an infinite number of time, I pulled out an infinite number of balls, and I'm left with 5 balls in the box, like so. Now, if you believe Cantor's set theory and transfinite numbers are an accurate description of how infinites would exist, there's no contradiction here. This is just the reality of the situation. You don't get to go in and say, oh, well, there's these different levels of infinity, because once again, these are set into a one-to-one correspondence with the natural numbers. So there's no actual contradiction here. But I think obviously this is absurd. There's something odd here, that you can't just change the number of balls by sort of, I guess not even reordering them, but basically choosing the numbering that you pick. So we have a few options to resolve this contradiction. The first thing to do is to just bite the bullet and say, okay, this is just how things work in infinity. You get something from nothing, and it is what it is. I don't think this is a good solution, to be honest. I'm just going to cross that one out. The second one you can do is say that you can't form an actual infinite from successive addition, which is what we did. We literally counted an actual infinite. I think that's problematic. You could also just make the argument that you cannot have an actual infinite metaphysically. Like, you could never actualize the infinite set of balls in the first place, and that was actually the problem. And you have some other options too. You know, you could say, okay, you can add to create an actual infinite, but you can't subtract from an actual infinite. But of course, I know Joe wouldn't like this, because this would create a distinction between past and future events, which involve successive addition and subtraction if you hold to an A theory of time. But still, it could work. I mean, you could make the argument you can count up to infinity, but you can't count down from it, and that's just a reality of infinity. Something a little bizarre about that to me, but I think you could make that argument. There's nothing necessarily on the surface, there's nothing that seems to be contradictory about it. Or you could maybe argue that actual infinities can exist, but not in a realm where things can actually be added or subtracted. I think Trent Horn makes this point where, it almost like there would need to be some sort of thing that would keep you, if an actual infinite could exist, from actually subtracting or from actually adding or moving things around. And that seems a little odd too. But I mean, you could posit that such a thing could exist in a Platonic realm. But I think in actuality, it's a little bizarre. But I think the best option here is to say you cannot form an actual infinite from successive addition. That seems to be the main issue with this analogy. If you're like me and you also doubt that actual infinites could exist metaphysically, that's kind of a different sort of thing. So that's kind of how you could solve that problem. Anyway, thanks for watching. Let me know what you think, and I'll see you in the next video. Peace.